All right, guys, how's it going? My name is Aaron McCanty. I'm going to be giving a talk on embedded system security and how you can take some lessons learned from the offensive world and apply them to make your code and software and hardware more secure in your development effort. Quick note, if you have any questions during the event or during the talk, post them in the chat along with the video. I'll do my best to answer them as we're going along, and other people might be able to jump in and answer as well. So let's go ahead and get started. So first of all, who am I? Like I said, cybersecurity researcher at Battelle. Battelle is a nonprofit research and development organization headquartered just south of campus on King Avenue, just a stone's throw away from OSU. My job, I specialize in reverse engineering and vulnerability research, mostly focused on embedded systems. So that is taking hardware, software, firmware, ripping it apart, figuring out how it works, and then figuring out how to break it. Kind of like working on a big jigsaw puzzle all day long. I'm also an OSU grad. I graduated from OSU with a degree in computer science. And you can check out some of the work that I've done on GitHub. These are two of the projects that I've been heavily involved in and use almost every day in my work. So agenda for today. We're going to talk about what is an embedded system, so we're all on the same playing field. We're going to talk about how embedded systems are attacked, how an offensive engineer goes about breaking into systems. And then we're also going to talk about how you can use some of those lessons learned to design secure systems and prevent your systems from being the victims of hacks in the future. So let's jump right into it. What is an embedded system? So classic presentation definition here from Wikipedia. Embedded system is a computer system which is a combination of a computer processor, computer memory, and input-output peripherals that has a dedicated function within a larger mechanical or electrical system. It is embedded as a part of a complete device, often including electrical or electronic hardware and mechanical parts. That's quite a mouthful, but essentially it boils down to embedded systems are small purpose-built computers. They're computers that are designed to do a particular task and function as a larger part of a larger system. So some examples of this, they are everywhere. Embedded systems are everywhere. IoT devices, Internet of Things, smart switches, routers, all those kinds of things. Cars are big embedded systems now, all kinds of systems interchanging and working together to function in the vehicle. Same thing with planes, phones, satellites, even medical devices now. They have Bluetooth-enabled pacemakers or surgery systems that surgeons can control from across the country that are just big embedded systems. So as you can see, they are everywhere. But they're just a computer, right? They have memory, they've got input-output, they've got programs, they've got operating systems, everything you can think of, in regards to a computer, they have, and that includes viruses. Viruses do exist and attacks do exist on embedded systems. They're not just a desktop or a server kind of issue. They also target embedded systems. And often embedded systems are kind of the weakest link in a network. So embedded systems are everywhere in your life, but when was the last time you thought to update the software on your router? It's probably been a while. It might not have been, since you've installed the router or set it up the first time. And now, when you're thinking about that, what about last time your parents did that? Chances are that was a lot longer ago than when you did it, and that's kind of scary to think about. That your parents are using these embedded systems and not keeping them updated, not keeping them secure. Embedded systems contain vast amounts of personal data. They're used to control critical infrastructure and keep people alive, as we saw with like the Bluetooth enabled pacemakers. But they're also a lot of times the last things we think to update. That's kind of a weird state of the world right there, where we are depending on these systems to do so many critical things, but we don't think to update them with the latest security patches. But that's okay, right? Surely embedded system developers know how to keep you safe. Well, we'll see about that. So, botnets are existing, routers getting hijacked. Oh boy, there's a Jeep that just got hacked. Meltdown and Spectre were big last year. Mirai botnet. Oh man, my coffee maker is now trying to get a ransom out of me. Oh geez, man, I guess this is fine, right? So obviously embedded systems are vulnerable. They're getting hacked all over the place. What happens when they are hacked? Why are people hacking these embedded systems? What are they using them for? The first question that comes to mind when I talk to a lot of people about this kind of stuff is they ask, is my TV spying on me? Is my Alexa spying on me? And while that's very possible, it's very unlikely that anybody is targeting you. And the simple fact of the matter is most people are extremely boring. You have to think about what the motivation is for somebody to hack into something. And usually that is some kind of political reason or financial reason, and not having to do with specifically targeting an individual person, unless you're, the CEO of a company, or, working with some, classified documents for the government. You're probably not going to be the target of, espionage or spying. More often than not, embedded systems are subscribed or are hacked and made part of a big larger botnet to use in distributed denial of service attacks. These are also called DDoS attacks. These are attacks meant to financially impact or disrupt a corporation or service. And the idea behind these attacks is you overwhelm a system with thousands and thousands of bogus requests, and you prevent any valid requests from getting through. This is a very common thing nowadays with big video game releases. If a new game is getting released and some organization wants to disrupt that release or impact the video game developer financially, they will DDoS their servers, preventing legitimate players from being able to log in and play the game. Now, the key with these kinds of attacks is they're dependent on thousands of unique systems for a prolonged attack. Now, why is that? The simple reason, these are pretty easy to defend against if they're coming from one source. A sysadmin just needs to blacklist all requests coming from that IP address, and then you're good to go. But if you have thousands and thousands of unique systems all attacking the same server, that's a much harder thing to defend against. And these attacks can be much longer, much more prolonged, and much more financially impactful. Another big thing nowadays is cryptocurrency miners, actually. Cryptocurrency like Bitcoin, Ethereum, incredibly interesting financial field to go into. But cryptocurrency, one of the big fundamental things is they need computers to do the math to mine Bitcoins. So Bitcoins are generated by doing some complex math, and if you use your computer to do that math, you can actually earn Bitcoin or other cryptocurrency by mining them. The thing is, though, doing this, mining Bitcoin, is barely profitable if you're paying for your own electricity. So many people are doing it these days. The cost is being driven down so much that it's barely profitable if you are the one paying for electricity. But if you can attack somebody else's system, install a cryptocurrency miner on their system, and then run it while they're using their electricity to pay for it, then you can start making some pretty nice profit. Once you don't have to pay for the electricity going in, everything coming out is pure profit there. So those are some of the things that they're actually used for instead of spying on you. Why are embedded systems attacked? First and foremost, they're a really easy target. Like we talked about earlier, most people don't update their embedded systems. They don't think to update them, which means bugs and vulnerabilities that were found years ago can still be extremely effective today. We see that a lot of the big botnets that are going around utilize flaws and vulnerabilities and hard-coded credentials that existed and were found 4 or 5 years ago and just have never been updated out of systems. Embedded systems are also extremely prevalent. There's a huge number of IoT devices, and that makes it very easy to build vast networks of botnets and cryptocurrency miners. And just drive that point home. How many devices do you have at home connected to your home network? Your TV, your car, your smart light switches, your Alexas. Everything can be attacked, and everything is vulnerable. And to compound on these issues, embedded system developers are often completely unaware about how their systems are actually exploited. How do you defend against something that you don't know how they are attacking? You're trying to defend your house against bugs by building a moat, but fail to realize that bugs can fly over the moat. That's that kind of thing there. So how can you expect to defend against attacks when you don't even know how the attacks are coming at you? So let's talk about that. Let's try to leave you guys with a little bit of knowledge gained here. So how are systems actually attacked? Just like any other computer, they can be attacked remotely across the internet. They can be attacked locally. If you have something like Bluetooth-enabled devices, have to be within 20 or 40 feet to actually connect to those devices. Another common thing is to jump from one compromised system to another. So some systems, you gain access onto one, and all of a sudden you can see a bunch of other systems. If you exploit a router, somebody's home router, then all of a sudden you can see all the other devices that are attached to their router and start going after those one by one. So an interesting thing here is that botnets are often created like a biological virus. So this kind of hits home nowadays with COVID going on, but the primary objective of every infected system is always to propagate and to ensure that it survives and spreads as much as it can. A botnet does not, if you have one node on a botnet and that node gets updated, then you've lost your access. But if you have 1,000 nodes, then one gets updated, it's not a huge loss for you. And also the kind of scary thing here is that modern reverse engineering tools make systems trivial to rip apart. And I'm going to show this in a couple slides here, but we can go from an idea about something to attack a system to finding an exploit within just a couple of minutes. We're using modern reverse engineering tools. So the field is the ecosystem is ripe for a lot of vulnerabilities here. All right, so how do we find the flaws? Researchers can purchase their own systems to gain access. So Amazon is a big help for when we're doing research on embedded systems, because if you find a system you want to look at, chances are you can grab it on Amazon and have it at your house within a couple of days. So think about smart home equipment or routers, really easy to grab on Amazon. Or you could just download a firmware update online. A lot of embedded system developers distribute their updates, their software updates, their firmware updates online. And those are pretty easy to find. You can just go to their website, look at their support pages, and download firmware for the systems you're interested in. And oftentimes, firmware is also distributed unencrypted online. So that means if you can grab it off the internet, you can pull it down, start pulling it apart, and look at the code that's running on the system without having to break any crypto or get around any security measures. Exploitable flaws can be found just by looking at code running on the system or the firmware. So you don't actually need hardware, in your lab to find a flaw. A lot of the times, our research at Battelle, we're able to find vulnerabilities just by looking at a firmware update we find online. So we don't even need to have Amazon deliver us the hardware in a couple of days. We could find a flaw even quicker and sooner without even needing the hardware. And again, I'm going to demonstrate this in a couple of minutes here. So let's take a look how easy that might be. First, we're going to take a look at Linux real quick. I know a lot of people in the audience right now might not be too familiar with Linux, but it's another operating system similar to Mac and Windows. So some might call it the operating system for nerds. Mac and Windows are designed for regular users. Think about your grandma and grandpa. They really need their handheld when using a computer, right? So these operating systems, Mac and Windows, are really easy to use, but they're extremely hard to shoot yourself in the foot. It's hard to find, and I know some people out there will be disagreeing with this, but it is actually hard to find a bug in Windows and Mac that will, say, crash your system or give you that blue screen of death. Those things are harder and harder to find every year. But that means that these operating systems are really, really bloated. They've got a lot of error handling. They've got a lot of programs and software that help people use them. And on top of that, modern operating systems require a decent amount of horsepower to run. If you try to install Windows 10 on your old desktop from 1995, it's not gonna be able to run. You need a significant amount of resources and power now to just run the operating systems. This makes it really hard to use these operating systems on resource-constrained embedded systems like routers and smart home equipment. Linux, on the other hand, is designed more for power users. These are the people that will say, I know what I'm doing, even though usually most of the time they don't. Linux is a lot harder to use. There's a much higher barrier to entry here. And it's incredibly easy to shoot yourself in the foot. But that being said, the size can be cut down drastically. You don't have a whole lot of error handling. You don't have a whole lot of programs that hold your hand, which means that this operating system, Linux, is ideal for resource-constrained embedded systems. You can compile Linux down to be incredibly small. You can strip out features that you're not interested in and make it run very quickly and efficiently on less powerful machines. So what do I mean when it's easy to shoot yourself in the foot? So this command, rm-rf/catpic.jpg, will remove one cat picture from your computer. This command, rm-rf/catpic.jpg, will remove all cat pictures from your computer, along with everything else. That one space between the slash and the catpic.jpg will mean that this command will now try to delete everything on your computer, every single file, which will ultimately destroy your system. So when you're using Linux, you're never more than one mistype, one space bar hit away from total disaster. But that makes it a lot more fun to use, right? So Linux has a lot of really useful built-in features. So on the command line, you can check what folder you're in by using that pwd or present working directory command. You can see I'm in the users, Mercanti, documents, presentations, embedded security files folder. You can also list out the files in that folder. So using the ls command, you can see I've got a couple of pics of my cat and dog. And I also have my password stored in plain text. I don't see any problem with that. I hope you guys don't either. There's also a really awesome utility built in called ping. So ping, you can type in a IP address or a URL. You can see if you're able to connect to that IP address or URL. Ping will tell you if you have a connection to that server. You can also download things directly from the command line using the command like wget. If you issue the command wget dogepics.com/dogepic.jpg, it'll download the dogepic.jpg to your computer. That's how I grab all my important files. There's also a lot of meta variables or meta commands that you can use on Linux command line. So one of these is the semicolon. Semicolon lets you chain two different commands together. So you could ping dogepics.com and then issue the wget command to download something if that is successful using the semicolon. So just a quick way of chaining two different commands together. Semicolon, it'll issue command 1, and then once command 1 is done running, it'll start with command 2. So that was our quick Linux primer there. So let's dive into an actual embedded system. So this is the Cisco Linksys E1000 home router. This is a really cheap consumer router. It's actually provided as the default router for some internet service providers. When you sign up for their service, they'll send you one of these. These are pretty old now, might not be used nowadays, but it's running embedded Linux. So there is this is a full working computer. It has a full operating system on it. It is running Linux. So all those commands that I talked about in the previous slide will work on this guy if you can get to a command line. A router is also a gateway from your home network to the internet, which means the bad guys can see this. This router is touching the internet, and routers act as a kind of a shield between everything on your home network and the internet at large. But that means that the bad guys can see the router. It also has enough computing power to mine about 2 cents worth of crypto a day. This thing will make you rich after about 1,000 years, but we'll talk about that in a minute as well. I'm going to talk about a flaw that was found by a security researcher named Michael Mesner. You can see his blog there if you're interested in checking it out after this. Like many routers, this router has a diagnostic page that you can use to set up the router, manage it, um, debug things that are going on. And one of the diagnostic tests that is included in the web interface here is a ping test. So with this ping test, you can insert a IP address or a URL and hit that button, start to ping, and the router will see if it has the ability to connect to it. Now that sounds a whole lot like that ping command that we talked about, in our Linux primer earlier. And as it turns out, it's basically the exact same functionality, right? So, like any good developer, the embedded system developers that created this router thought to themselves, "Hey, why should I recreate a ping utility when there is one that already exists on the Linux system that I'm running on?" So how this is implemented is the developer will take whatever you put in this IP or URL address field, slap it into a command line utility tool here that just uses the built-in Linux ping command with the IP address or URL that you supplied. That means if you put in the IP address 192.168.0.1, it'll issue a command on the Linux command line that says ping 192.168.0.1. Now, this is really awesome because the developer found a way to shortcut the development process. They didn't have to implement their own ping. They reused the features that were already there. Everyone's happy, except this is something that's really easy to take advantage of. So we had talked about those meta characters in Linux before. So if you issue or if you input something as simple as 192.168.0.1 reboot, that will correctly ping 192.168.0.1. But as soon as that ping is done, it'll issue the reboot command on the router, which will, as you might imagine, reboot the system. Now, this happens because the developers blindly trust everything that is entered into that text field. So it's a pretty easy feature to fix and get around, but it did exist on this router and was able to be found. And rebooting the router, not very interesting, but we can issue the command to download a crypto miner, and then all of a sudden we've got a cryptocurrency miner making me a whopping 2 cents a day, using somebody else's electricity to pay for it. So just like that, as simple as that, we can install a crypto miner on somebody else's embedded system. So that was a pretty easy flaw to find. I'm going to talk about a little bit more of a complex one. So this is another router, D-Link DIR 890L. This is a $300 consumer router. It does kind of look like a spaceship, though, doesn't it? The more expensive these routers get, the more out there they look in design. This thing is also running embedded Linux, so it also has all the built-in features that we talked about previously. It's got a full operating system. It's a complete computer running inside this box. Also, again, because it's a router, it's the gateway from your home network to the internet. Bad guys can see this. This guy is cash cow, is what I like to call it. Can mine up to 6 cents worth of crypto a day. So we're really raking in the money now with this one. And the flaw that I'm going to talk about here was found by another researcher named Craig Hefner. You can see his blog there where he talked about this flaw. So before we get too into it, something that this router takes advantage of, there's a protocol called the Home Network Administration Protocol, or HNAP for short. This is a protocol used by D-Link router for their easy setup program. So instead of making their users go into the web interface to configure their router, set it up the first time, they have a program that you can run on your computer that will submit requests and commands to the system, to the router, to set it up for you without you having to go through all the settings yourself. Really easy to use for setting it up at home for non-power users. You can send your commands to the router through a series of web requests instead. The basic procedure here is when the program runs, it first requests the device info, figure out what kind of device it's connecting to. It then sends a login request to log into the router, so you can start messing with the authenticated settings, the authentication controlled settings. And then you can send commands to set up your device by, creating your Wi-Fi access point name and setting up the password for it so that people can connect to it. You can do that all from a utility program you can run on your laptop or desktop instead of having to go through those administration web pages. Really useful, but not without its own flaws. So let's go ahead and rip this thing apart. So D-Link is kind enough to provide their firmware online for easy download. I've gone ahead and done that. So you can see that I've got, if I list this out, the firmware for the D-Link DIR 890L, or hardware version A, firmware version 1.03.B07. They released it as a zip file, so I'm going to go ahead and unzip. And we can see inside of that zip file, we had a PDF that is the release notes for this version of the software. So we can take a look at that and see how to install this and what changes they were made on in this version of the firmware. We also see this binary file here. So that is going to be the binary file that contains all the code that actually updates the router. But if I run a command like file on it, we can see that this is just raw binary data. It's just ones and zeros. My Linux system has no idea how to interpret this file. So this is right where most embedded system developers will think that researchers stop, right? They're presented with a binary file that contains raw data. They don't know how to interpret it, so they're just going to stop and not bother with it, right? How can they possibly figure out how to interpret this raw data? Luckily, there are a lot of tools that help security researchers with this. One of them is called Binwalk. So Binwalk is a really awesome tool. It knows how to interpret all kinds of different files. And it'll take a raw binary image, like this firmware image that we have here. It'll scan through it and look for every single possible file type, file version that it can find, and start extracting them out. So I'm going to go ahead and do run Binwalk on this guy. Ooh, maybe I don't fat finger it. Okay, so you can see Binwalk is starting to find some stuff. It's starting to pull stuff out. It actually creates this extracted folder for me, so I'm going to go into that. Inside of here, we see it found a SquashFS root file system. So SquashFS is a really common way to compile Linux down to be very small. So if I go into this SquashFS files folder, start looking at files in here, we can see we've got the full root file system for the embedded system here. So if I look in the binary the bin folder, you can see that it has a bunch of programs that are running on the thing. We can also see it's got etc/dev/htdocs. If I go into the htdocs, that's where a lot of the interesting stuff is. So in here, we've got a couple of binaries, one called CGI bin, one called fileaccess.cgi. If I look inside of the web folder in here, you can see a bunch of the HTML pages, mobile my D-Link, mobile firmware updater, firewall.html. So these are all the web pages that you can use to actually interface with the thing when you go to the diagnostic or the administration web page. But the most interesting thing here is the CGI bin. I'm going to take a look at it using a different tool. But if I real quick on file on CGI bin, we can see that this is a 32-bit ELF executable. So this is the Linux version of EXEs. So it's just an executable that runs on a Linux file system. we can see a whole lot of information about this, but the important thing here is that it's an ELF 32-bit executable. So I'm going to jump back over to my other box here. So I'm going to open that CGI bin binary in another tool. This one is called Ghidra. So Ghidra is a reverse engineering tool that was released by the NSA open source last year. So it's a really useful tool, and we can use it to rip apart this binary very easily. So we talked about the HNAP protocol earlier. So I'm going to go ahead and take a look and see if there's any strings in here related to HNAP. Again, if I type correctly. So we can see here, there are a couple of interesting strings here. One that is includes HNAP1/get device settings. One is login, one is logout. So it does look like this binary is handling some of those requests that are being sent to manage the system. So I'm going to go ahead and take a look at where this device settings string is being used. So jump in here. So this is where Ghidra becomes really useful. On the left-hand side here, these are the ones and zeros that are contained in that binary file. So that is the actual compiled code that is running on the system. And then on the right here, Ghidra is able to take those ones and zeros and turn it into C pseudocode. So this is a lot easier to read. You can actually pull out function names like stir, or get env, a very common program or function to call when doing web requests. And this is a lot easier to look at than the ones and zeros over here. And now doing this, you can start finding some pretty interesting stuff, right? So the first thing this thing does is compare one of the environment variables to this string, HTTP peernetworks.com, HNAP1 get device settings. Then it does the same thing with this other string that has the login thing, the login string. We can check out some of these other functions. So down here, it's doing some processing. Here, you can see it prints out a bunch of text like unauthorized or moved permanently or 404 not found. So it's doing some processing on the data that's coming across. This is a little much to handle. So I've gone ahead and, well, actually, I'm going to talk about one more thing here. One other thing that we can see, they use another really common function call down here called system. Now, system is exactly what the Linksys router was doing before. It takes a input if you want to run something on the Linux command line. It will take that, whatever you want to do. If you call system on that string, it'll take whatever string you pass the system and run it directly on the command line. So directly above this, we can see it's building using sprintf, a command to run on the command line and using these %s's and some SOAP action. And SOAP action is one of the environment variables that is passed over through the HTTP request. So what this tells me, and I know this is making a lot of leaps for people that have never seen this before, but I can probably control the SOAP action that is used here. If I can control the SOAP action that's used here, then that is used to build a command line command that is sent through the system command to run on the Linux command line. So that's where that ping vulnerability that we saw in the last example came from. So I went ahead and made this a little bit easier to read. So here we go. So what this is doing, what this function is doing, it's grabbing a action from the web request. It's checking to see if the action contains this get device settings string. If it does not contain that string, it does an authorization check to make sure you're authorized. But if it does contain that string, it skips the authorization check. Now it does that because the get device settings is one of those very few, or one of those couple commands that you need to be able to issue before you log in to be able to figure out what device you're talking to. So you don't need to log in to issue that request. So then what it does is search for the last instance of slash. So in this case, if you pass in that get device settings string, it'll grab everything up to that last slash and then build a string down here using that sprintf call and then calling system with it. So that builds a command that just issues the get device settings .sh command on your command line. Now, that's not too useful to us unless we can do something other than issue the get device settings command. There is a flaw here that will allow us to do that. And the big thing here is this call to stir. So stir, for those that don't know, checks to see if a string contains another string. So this is checking to see if the SOAP action string that we pass in contains this string. It's not checking to see if it matches exactly. It's just checking to see if it contains that string. And that's something that we can use. That's a flaw that we can exploit to issue additional commands. So bingo, there we go. A command that contains that get device settings strings will skip the authorization check. So if we issue a command that says http peernetworks.com/hnap1/get device settings ;reboot, it'll grab everything after that last slash up to and including the reboot and put that in a command on the command line. So we can do the exact same thing we did before. Instead of doing reboot, we can issue our wget command to download a cryptocurrency miner. But the flaw here is the developer should have used stir compare instead of stir. So stir compare, this strcmp, checks to make sure that a string matches exactly, not if a string just contains the string of interest. That would have prevented this flaw from being able to be used. Either that or make it so that you can't issue this command without logging in first. That would also have solved things. A lot of ways to solve it. But what's clear here is that the developer had no clue what command injections were, had no idea that this was even a possible attack, or else they would never have used that stir function call. That was a lot to take in, I'm sure. There's a lot to learn from there. Well, I wanted to leave you guys with some actual actionable information, some stuff that you can actually take home and learn. Number one, you have to understand the attacker. Have to understand how your systems are going to be attacked and what are the motivations of an attacker. Biggest recommendation here is to not shut yourself off to the offensive security world. There's a lot of really great conferences out there. Cybersecurity Days at OSU is one of those. Black Hat DEF CON out in Las Vegas is another great one. Another great two. But there are security conferences going on all the time where security researchers talk about how they are attacking systems, what flaws they're finding, how they're going about reverse engineering systems. Open yourself up to that. Be willing to learn about the other side of the coin. And you'll be able to understand how your system is being attacked. And once you understand how they're being attacked, you can start figuring out how to design them better. The other side, next tip, make sure you spend the money to actually do things right. Shortcuts lead to bugs. That developer that reused that ping functionality on that first example, he probably saved a lot of money from his project because he didn't have to re-implement that feature. But if he had re-implemented it, he might have not included the same bugs we saw there. Also, another great tip: create a red team, or look for a red team that you can hire out to investigate your systems and software before a adversary does. Not all hackers or offensive security experts are the enemy. There's often a negative stigma applied to people that do this kind of work, and that's something we really need to move away from in order to move the field forward as a whole. And another great thing you can do with this is you can find the easy bugs before the bad guys do, before you become financially responsible for a bug, or before your medical device gets hacked and costs somebody their life. You need to find those bugs before the bad guys do. And the last piece of advice that I have coming out of this talk, you have to realize that you can't stop a determined attacker. No matter how much you try to hide it, no matter how much you try to obfuscate your code, the logic that you have running on your embedded system will always be present on that embedded system. There will always be a way to reverse engineer, to rip out the brains of the system, the brains of the software, to find the logic and actually see what's going on. You can't hide it entirely, but you can make your system less appealing. If you're able to demotivate an attacker, they'll go after an easier target. So from a user perspective, if you keep your systems updated, then that immediately makes your systems less targetable, less interesting for attackers. They'll just go after your grandma's that has not been updated in 15 years. And also if you're a developer, you can, don't be completely turned off from trying to obfuscate your code. If you make it difficult for an attacker to look at, they're just going to give up and look at an easier thing. So one fun way to do that, this is another project that we've talked about or done at Battelle. If our goal is to demotivate a reverse engineer, us being some of the best reverse engineers in the industry, we've got a pretty good understanding of what it takes to demotivate a reverse engineer. So what if you try to use their own tools against them? So there are some tools you can assume that a reverse engineer is probably going to be using. And if you reverse engineer those and learn how they present data to their users, which would be the reverse engineers, then you can structure your code in a way to, quote unquote, exploit that. So this is another tool we've got in GitHub if you want to take a look at it, play around with it. One of the most common tools that reverse engineers use is a control flow graph. So this takes those ones and zeros that the program is made up of and breaks it up into distinct basic blocks and then traces the connections between them. So in this example, we start the function at the top, it does a couple of operations, and then has some kind of decision, depending on the result of one of those operations. It'll either go down this green path down to this left here or go down to this red path on this right. So that's like an if statement in code. So breaking code up like this, you're able to pretty easily, make inferences about the code, understand the structure, understand how things are operating, and effectively reverse engineer the system. But if you can figure out how the tools are displaying these basic blocks, then you can try to structure your code in a way that draws a picture. And if you are a reverse engineer and you're reverse engineering a system, and the first thing you see when you pop open your code that you're trying to reverse is a skull and crossbones or something else, I'll tell you from experience that would make me very, very demotivated. So kind of a fun way. This approach does add a lot of additional bloat to the code and makes it very inefficient to run. But it is a fun thing to play around with. So again, if you want to check it out on GitHub, we've got it up there. And with that, I'm going to leave off. So again, if you have any questions, please feel free to drop them in the chat. I'll be hanging around to answer them for you. And aside from that, hopefully you guys learned something new here. I know this is a lot to take in, very technical for some people, but hopefully you learned something new, and hopefully that can be used to help you design and better and more secure systems in the future. So thank you guys very much.